Welcome to another video in Nash School's data science series. In this video, we are going to continue looking at a topic in probability. If you are a data scientist who has been reading some research papers in this field, very likely you would have come across the terms omega f comma p in some research papers. This can be sometimes baffling because these are somewhat technical terms, and people who have done elementary probability theory are unlikely to have come across these terms in their curriculum. Let's delve a bit about what these terms are in this video. To recall, in our previous video, we had talked about the three important factors to describe a random experiment. The first factor is the sample space, which is the set of all outcomes. The second factor is the set of all events, which are combinations of outcomes to which we can assign meaningful probabilities to. And the third factor are the probabilities that we assign to these events. With these three factors, we can totally understand any random experiment. Let's delve a bit deeper into these factors for a case of a simple die experiment. In a simple throw of a die, we know that the outcomes are the numbers from 1 to 6. And events are combinations of these outcomes. So there could be one event which is null set, which is nothing, none of the 6. For example, if someone asks you the question, what is the probability of getting a 7 in the throw of a die, then basically no such outcome is possible. So you can say probability of null set is what the event that's corresponding to this question. So the probability is 0. Someone could ask the probability of getting a 1 or probability of getting a 2. Then you can basically say these events are those single outcomes. Then you can combine two of those outcomes. You can say 1 and 2, probability of getting a 1 or a 2. Those are every two possible combinations, every pair of outcomes can be called an event. So you can have 6 choose 2 events by combining, by looking at pairs of outcomes. And you can have triplets of outcomes. What is the probability of getting a number which is less than or equal to 3? Then you look at the triplet 1, 2 and 3, and you have 6 choose 3 triplets of outcomes, so on and so forth. So you can enumerate 64 different events in the simple die experiment, which is basically all possible combinations of the 6 outcomes that are possible. And obviously you can assign probabilities to all of those events based on the fact that the outcomes are equally likely. So now the thing is, everything is easy, nice and easy in this experiment. But let's just try to complicate things further by looking at a different random experiment. Let's say you are playing a game with your friend, and your friend is basically asked to choose a number between 0 and 1. And your duty is to assign probabilities to the numbers that he might say in the first place. Before the friend gives a number, you should be able to assign a probability to that number. We know that there are infinite possibilities of the friend picking a number between 0 and 1 because there are infinite numbers between 0 and 1, infinite real numbers between 0 and 1. So let's think about what probabilities you can really assign. Say if you assign a probability of say 1% of him saying 0.5, okay, yes, 1% is meaningful, but then he's equally likely to say any number between 0 to 1. And if you're saying 1% to 0.5, then you have to assign the same 1% to 0.75, same 1% to 0.7, same 1% to 0.65, so on and so forth. But that wouldn't make sense because the total probability must add up to 1, and you can't go on assigning 1% to every single number between 0 to 1 because there are infinite numbers and the total probability is going to shoot up to over 100%, which is 1. So, and then you say, hey, yeah, that doesn't make sense. So I won't be able to assign any probability. So I'm going to say 0%. So if you say 0%, then you are going to uniformly assign 0% to all real numbers between 0 to 1. So if every single number is assigned 0% probability, which again doesn't make sense because the total probability must add up to 1. And the friend eventually will indeed pick a number between 0 to 1. So how is it that you assign 0% probability to a number that is eventually going to pick in the game? So that 0% is also not meaningful. So the problem here is that the sample space, unlike the case of a die, is infinite. So you won't be able to assign any meaningful probability, not 0%, not 1%, not 2%. No meaningful number can be assigned as a probability to a single number in the interval 0, 1. So the next question is, hey, do we admit defeat? I mean, do we just say it's not possible? And this is where the mathematician comes in and says, yes, you cannot assign probabilities to individual numbers between 0 and 1 in this game. So he just says, no, not measurable, which is the mathematician's way of accepting defeat in this challenge. Then obviously the next question is, what is the best thing we can do given that we cannot assign probabilities to individual numbers? The next thing is something called the open interval. So you choose a very small interval, however tiny it can be, and then you ask the question, what is the probability of your number, of your friend choosing a number in this open interval? Obviously, the smaller the interval, the smaller the probability that the friend's number will lie in that interval will be. If you can choose a big interval, let's say 0 to 0.5, and there is a 50% chance that the friend is going to say a number between 0 to 0.5, and a 50% chance he's going to say a number between 0.5 to 1. So the probabilities are easy to compute. They are simply the length of the interval in this case. So the mathematician here says, yes, you cannot assign probabilities to small numbers individual numbers between 0 and 1, but you can consider any small open interval and then assign the length of the open interval as the probability of your friend picking a number in that open interval. And that is the best we can do. This is the basic idea behind measure theory. So now, are we done yet? Not exactly. So how many such open intervals can we construct? So for example, if you consider 0, 1, you can split it into finite intervals. You can say 0, 1 over 2, 1 over 2 to 1. Or you can split it into 4 intervals, 0 to 1/4, 1/4 to half, half to 3/4, 3/4 to 1. So you can split it into small finite intervals, and then these intervals will sum up to the overall 0, 1 interval. But mathematicians won't be happy about that. So the question is, obviously we know that splitting it to infinitely many combinations is not working. We won't be able to assign meaningful probabilities. Splitting it to finite open intervals obviously works. It's just combinations of these finite intervals. The length of the finite interval is the probability, so on and so forth. But mathematicians' curiosity is going to lead us to the question, can we do something more than finite? And that something more than finite is what's called countably infinite. That is, you can create situations where you can divide this 0, 1 interval into countably infinite many intervals and still assign meaningful probability numbers which add up to 1. To see this, just consider 0 to 1 and do an iterative process. So in the first step of the process, divide 0, 1 into 2 intervals, L1, L2. L1 is 0 half, L2 is half 1. In iteration 2, you go to R1 and repeat this process. You again chop R1 into 2 halves, L2, R2, L2 being half to 3/4 and R2 being 3/4 to 1. And in step 3, you repeat the same process for R2, which is 3/4 to 1. You chop it into 2 halves, left half label it as L3, right half is R3, and in iteration 4 you split R3 into 2, L4, R4, so on and so forth. So you are basically splitting 0, 1 into infinite disjoint open intervals, which is basically L1, L2, L3, L4, which progressively diminish in size as you keep progressing in the iterations. But you can express 0, 1 as a disjoint union, as a union of these disjoint L's, L1, L2, L3, and so on, and you can assign probabilities, which is basically the length of each of these intervals. And we know from geometric series that the length of these intervals add up to 1, which is half plus 1/4 plus 1/8 plus 1/16 plus so on. That series adds up to 1. It's a standard result from geometric series. So what we have done here is that we have said not only is it possible to divide 0, 1 to finite open intervals and assign probabilities, it's also possible to divide 0, 1 to countably infinite many intervals and assign probabilities to these open intervals. It's a lot of information, so let's recap. So in a die throw, we had a finite sample space. We can assign probabilities to all possible combinations, the power set of this sample space, and all of them can be events, and we can assign probabilities to events. When the sample space is infinite, let's say 0, 1, we said it's not going to be possible to assign probabilities to all possible combinations of the sample space because no such meaningful probability numbers really exist. And what we saw is that the best we can do is to chop it into open intervals and assign probabilities to open intervals, and these probabilities are the lengths of the open intervals. And last we found that the open intervals, this separation of this interval of this 0, 1 to open intervals need not be finite, but you can have infinite disjoint open intervals adding up to the interval 0, 1, and you can still assign meaningful probabilities. But the only condition is that the intervals have to be countably infinite. If it's uncountable, then no, you won't be able to assign probabilities. Let me leave you with one another example. Let's consider another game here where the friend is not guessing a number between 0 or 1, but is given a coin. So when he's given a coin and he's asked to find head or tail, say, hey, it's a discrete experiment, it's a finite sample space. What's the problem with this? The problem is that the friend is not tossing the coin just once, but he's tossing the coin infinitely many times. So you're giving them the coin and then he's just going to keep tossing. And then he's going to note down the results of all his tosses on a piece of paper. And your job is basically ahead of the experiment to give probabilities, to assign probabilities to the path, to the list of to the sequence of head tails that the friend is going to come up with. So if it's all heads, then there is some probability to that. If it's all tails, there's some probability to that, so on and so forth. So can you assign meaningful probabilities to such paths? So obviously there are infinite, since the number of coin tosses is infinite, there are infinitely many paths, and it's not going to be possible. We are back to a similar predicament as in the previous experiment, and we won't be able to assign probabilities to all of these paths. So since we are not able to assign probabilities to all of these paths, what is the best we can do? What is the largest set of events we can assign meaningful probabilities to? If you have come across and studied measure theory, then you will perhaps know the answer. But if you're not, if you're listening to these ideas for the first time, and if you're intrigued, then perhaps you can think about this problem and think about what is the best we could do in this kind of experiment, and leave your thoughts in the comments section. And in case this is really intriguing, I'll be happy to post a new video discussing this example and the set of events to which probabilities can be assigned to in this example. Thank you.